In this session, we're going to look at binary data files. Binary data files are those that can contain any kind of data. So we might have floating point numbers, we might have integers, we might have structures, we might have the contents of arrays. Any kind of information or combination of those types of data can exist in a binary data file. Remember that they're usually a little bit smaller than the equivalent ASCII files, and that's because we don't need the formatting that's associated with our ASCII or text files. The one drawback to binary files is that they're system dependent. So if I create a file on a PC using a particular platform, then I need to make sure that that file is read on that same type of platform. They are good, however, for large amounts of data. When we're working with binary files, it's exactly the same as working with text files, except for two main differences. We're going to declare the file pointer, open the file, verify that it was opened properly, do the read or write, and close. So that looks the same. So what's different is in defining the mode. So we notice here that there's a B included with the read. The same thing would show up for the write. The other thing that's different is the actual instructions or functions that we're going to use in order to do the read or do the write. So let's look at reading from binary files first. Here we can see our declaration of a file pointer. We're opening it, and here we've got that B defined in our mode saying we're going to read from a binary file. Next, we check the file pointer to make sure it's not null. Then we look at our read instructions. So here we're going to use the F read. So the F, by now you know, stands for file, and the read means we're going to read from the file. In order to do that, we have 4 parameters. The first is the address of the variable where we want to store the information we're reading from the file. Next comes a definition of how big that variable is. So if it's an integer, it's going to be 4 bytes or 2 bytes depending on the platform. If it's a structure, it might be upwards of 60 or 70 bytes, maybe even larger than that. So we have the variable, the address of the variable, and its size. Then we identify how many of this type of variable we're going to read. So often that's just one. We'll read things one at a time from the file. But there is the option to read 6 structures at the same time, for example. Finally, we have to identify the file that we're working with. So here we're back to our file pointer. The process for writing 2 binary files is almost identical. We start with our file pointer declaration. We open our file. Notice here we're writing to a binary file, so the B stands for binary, the W is for write. That gives us our file pointer. We check to make sure it's not null. Then we're at our write. So here we have F for file, write for the operation that we're going to do, and it is almost exactly the same as what was in our F read. So the address of the variable that we want to write to the file, how big that variable is, how many of them we're writing at once, and our link to the file. And finally, down at the bottom, we have the closing of our file. Remember, it's absolutely critical that you use that F-close if you're writing to a file, and it's good practice to use it if you're reading from a file. Let's take a look at an example here. Here we have a structure declared that indicates we have an array of structures. The structures have some strings in them. They have an integer value and a floating point number, and we can see we have 5 elements in this array. So it looks like we have a database that's keeping track of information about parts, for example. If we look at the code now, we can see that we're opening a file to write, and it's going to be a binary file because of the B that's specified here. Our file pointer is F pointer. We check to make sure that the open was successful, and then we're going to write information. So let's look at what we have here. We have the address of data. So that's the address of the structure the array of structures that we've defined up here. Then we're going to use the size of operator, and that size of operator is going to calculate exactly how many bytes that are in data. So data is our variable that's defined here. Data is an array, so it's going to calculate how many bytes are in the array. We're going to write 1, in other words, 1 times this number of bytes to this particular file. So this is going to write all of the information in this array of structures into a file called file name D. Now let's look at the code that we would use to read that file. So we have a file pointer. We're opening the file called file name D. This time we're opening it to read a binary file. Again, we check to make sure that the open was successful, and now we're going to use the fread command. So we have that information is going to get read into a variable called data1. The size of data1 is going to be specified. We're going to read 1 of that and file pointer. So what does data1 have to be? Well, it has to be big enough to hold the same information that the structure we defined up here did. So data1 has to be an array, and it has to be big enough, in other words, have enough elements in the array to hold the equivalent of data, what was defined as data. Then finally, last thing, we're going to close that file. But now, in data, or data1, we have all the information that was written to the first file. So once we have opened the file, read in the information stored in that binary file, and now we're ready to use it, how do we go about doing that? So let's take a look at some of the things that might be useful for us. The first instruction that we have here is very useful. Let's take a look at the 2 parts. So the first part, and we're doing a division operator, so the first part here, this is giving us the total number of bytes in the array. Say we're doing size of data1, and data1 was our array. Now if we look at the second part, it's saying size of data1 element 0. So this one is telling us the number of bytes in each structure. So if I take the number of bytes in the array and divide that by the number of bytes in each structure, what that's going to give me for number 1 is the total number of elements in my database, which is going to be very useful for us if we want to loop through each of the elements from element number 0 through element number 1. So that's what we're doing in this for loop here. What are we going to do with those? We're going to print the part number, the name of the part. So we're at part number, and now I've done I+1 instead of I, and that's to make it more user-friendly. So instead of saying I'm at element number 0 of my database, I'm saying I'm at element number 1. Now here, I'm printing the name of that element, the floating point number, the integer, followed by the floating point number. And if we look over here, this is actual output. So we have part number 1 was called part 1, and the integer value stored was 111, and the measurement was 11.1. And if you remember from a couple of slides ago, we had part 2 with 222s, we had part 3 with 333, part 4 with 444, part 5 with 555. Now if we look at this section down here, what happened to those? What's this garbage that's there? Well, it turns out that my array, which was data in my program where I was writing to it, actually had room for 10 values. I only happened to use 5 of those, so the other 5 were sitting empty. They had the garbage that was stored in those memory locations before. So when I'm printing this, number 1 is going to get calculated to be 10. I've looped through, I've printed the 5 valid ones, but now I have 5 garbage ones as well. So one of the things that we can do to help make sure we're not trying to use garbage elements, we'll take a look at on the next slide. Now if we look at the first instruction we have here, you can see that we've changed things up a little bit. Here we're calculating number the way we did before, the size of the array divided by the size of the element, and then we're writing that number into the file. So that's going to give us a reference point. But if we think about it, this calculation we're doing up here is really calculating the total size divided by the size of one element. That's going to tell us how many elements there are in the whole array. But it's not going to tell us how many we've actually used. So what we want to do instead of that is we're going to eliminate this line, and we need to have somewhere been keeping track of how many elements we've used. And usually that's the index. So somewhere along the line, as you've been adding elements, you've been keeping track of an index. And that's what we want to use here. So that number should be assigned the index that we've got here. Then, when we write that number into the file, that's going to tell us how many valid structures that we have. So down here, we open our file. The first thing we read is how many structures we have, and we can load those in. We now have a value, number 1, that will tell us how many elements to print. So to recap, when we're working with binary files, our file open to read or to write has to include a B to indicate a binary file. Then when we're reading from the file, we're going to use fread. We're going to say the address of where we want the file, the variable we're reading to be stored, how big it is, how many there are, and our file pointer. When we're writing, again, we're going to provide the address of the value we want to write, how big it is in bytes, how many of them, and the link to the file.